So maybe we wait for another 2 minutes. Some more participants can join. Okay, so good afternoon, everyone, once again, and welcome to the today's lecture. I also welcome our today's speaker, Dr. Ramchandra Yella from Department of Physics, University of Hyderabad. It is his mm, kind consent that he kindly agreed to talk upon the one of the important aspect for the quantum sensing or the quantum technologies. Basically, he will be talking about states of light, including Fock states, coherent states, squeeze states, and he is the expert, or he has expertise in quantum optics, cavity quantum electrodynamics, nanophotonics, diamond nanophotonics, and quantum plasmonics. Both the lectures will be uh, given by Dr. Yella, and now I would like to invite our expert to take over and start the talk.
Yeah, can you hear me?
Yes, sir, we can hear
Yeah,
you.
right.
So now we'll stop presenting and you can share your slides.
Okay, all right.
And sir, maybe you can have 5-minute break, miss after 1 hour.
Oh, it's okay. So which is let's say
Roughly 3 o'clock.
2:55. Just let me or anyway, I'll stop at 2:55 for 5 minutes. Then again, I will start. Is it fine?
Yeah, thank you.
Yes,
Thank
sir.
you.
Yeah. So is my slides are visible?
Yes, sir.
Okay, so before I start my talk, okay, so thank you for your kind introduction, sir. Actually, thanks for giving me opportunity to present our works as well as about this quantum states of light. And I want to emphasize on that I am originally experimentalist. So what I describe here is really we are measuring in our lab one of these quantum states, which I'm going to discuss in detail. If anybody is interested, of course, contact after the lecture. But as you know that it's not possible to discuss all the details of experiments, but I will give a glance what we have and what kind of things we develop towards measuring the describing the states of the light. So, okay, that's I will start my talk with this. First, I will give the theoretical outline, then the corresponding experiments, how difficult it is, just I will explain, and how to realize experimentally. And I'm happy to tell that we are sort of a lab where we have the state-of-art facilities in the country where no other place had. Those facilities also I will briefly show at the end of my talk. Okay, thanks for the opportunity, sir. I'll start my talk.
Yes, sir. Thank you so much.
Yeah. So my slide is visible, right? Right?
Right, sir. It is
Yeah,
visible.
right.
It is
Let's
now full
let's
screen.
start. Okay. Yeah,
Okay.
my dear colleagues and friends or the students, today I'm going to talk about the quantum states of light. First of all, before we go to the really the Fock states or the number states or the coherent states or the squeeze states or any other states of the light, and first we'll start with very, very fundamental. Okay, so what we have been sort of a learning or already learned that uh, so what you have learned is that when see here quantum states of matter, you have already know that how to quantize the levels, energy levels and all the stuff, but here what we are talking is the quantum states of light. So those kind of description is usually when you have a light and matter interaction. So one component is treated semi-classical, where this light is treated as a sort of a wave nature, and we studied the interaction between the quantum system, where you have a quantized levels with a light. But now, what is the topic of today is that it's a quantum states of light. It's not the matter. We are going to describe the quantum states of light or the quantum states of the radiation, which means that the light itself is quantized. So we need to quantize the field itself, electromagnetic field, which is the light. Okay. So to quantize the light, so basically the fundamental thing we start is that harmonic oscillator, which is in this case is a quantum harmonic oscillator we use. So what you are trying to say is that when we are learning the quantum harmonic oscillator, so we are trying to describe the position momentum in terms of the creation and annihilation operators, which is a and A diagram, right? So if A is act on some state, it will annihilate the state. If A dagger is act on some state, it will create or the it's like a ladder operators. One is going for up and another is going for down. So, which means that the light is, to say this quantized, in order to quantize the light, the field, that you need to write the field in terms of A and A dagger as what we have written as a quantum harmonic oscillator. That is the essential point. Okay, so which means that we need to apply the quantized harmonic oscillator, which is a quantum harmonic oscillator, to quantize the electromagnetic fields. Okay, so that's where the quantum states of light comes into the picture. So which means that light is a quantum harmonic oscillator. So then the moment you say it's a quantum harmonic oscillator, there are two powerful things. One is the left hand side is the energy is quantized in the units of h cross omega. It's a 0 point energy, which is a which when n is being 0, then you are going to get it's the energy is going to be a of h cross omega, which means that you do not have the energy which is less than this. Okay, always you landed up the energy, minimum energy is that 1 or 2 h cross omega. That is a one side. The other side is that, as you know, that it has to be satisfy the Heisenberg uncertainty principle. So the position and the momentum is delta x and delta p, which is basically the variance in the delta x and uncertainty in delta x and uncertainty in delta p. That should be greater than or equal, like or equal. It's h cross by 2. So these two things are very, very important. So we will describe these two when we are describing different states of a light. Okay. So majorly the classification has been started based on the photon statistics, the different states of light. So where the delta n, this is being the standard deviation. If you take a delta n whole square, basically it's a variance. So the variance, which is a delta n whole square, is equal to average value of n square minus average n whole square. That is basically based on that delta n, which is a standard deviation, or the delta n whole square, which is a variance, the statistical nature of the photons which are coming from the source. Okay, so they have categorized into three, which is a sub-Poisson statistics. Suppose that if the photons which exhibits the sub-Poisson statistics, then that light, what's called, it's the Fock state. The quantum state of that light is called Fock state. So in the Fock state, it's a sub-Poissonian means. What it is usually means is that the standard deviation is less than the square root of n average. So which means that the variance, or the standard deviation, is less than the average. So that means that you have a definite number of photons. Okay, so therefore you have a less photons. Often in this Fock state, usually it is generated from the single photon sources. The sources can be a single atom or the single quantum emitter, any sort of a single quantum emitter. So the experimentally realizing this part of the system is quite challenging, because you have to remember that you need to have a single photon source in order to exhibit the Fock, to represent in a Fock state of the light. So which follows the sub-Poisson statistics. Then the second one is the Poisson statistics, which we most of us uses in the any typical optics lab, which is a coherent source, which is a laser. In the laser, what will happen is that in the coherent source, when you have a standard deviation is exactly equal to the square root of n bar, which is the average number. So that will follow the Poissonian statistics. The Poissonian statistics is that you have the probabilities and all the things I will discuss in further. But in experiments, examples are the laser. So the laser photon statistics which exhibits is that it's a Poissonian distribution. So often most of the cases, people confuse with Poissonian and sub-Poissonian. Poissonian statistics are light, so you can get the sub-Poissonian. What I mean is that the Poissonian statistics, you have a number of photons. Like Poissonian statistics means the zero number probability is more compared to the photon number one. By alternating the laser pulse, so people often think that they can get a single photon sources, which is not quite correct. Okay, this is the essential difference. This is the essential difference between the sub-Poissonian and super-Poissonian. The another states, which is described as a thermal states, usually we see it from the any discharge lamps or the tube lights in the fluorescent lamps and all the stuff. That follows the super-Poissonian statistics, which means that you have a delta n, which is greater than your average photon number, square root of average photon number. So you see the difference. In the case of Poissonian, it is equal. In the case of super-Poissonian, it is greater than. In the case of sub-Poissonian, it is less than. So the second case and the third case, the realization of the experiments are rather easy compared to the realization of the experiments in the Fock state. Because to realize the Fock state, you really need a single photon source. That's where the single photon means you need to trap a single atom or a single ion or a single molecule or a single quantum light source. Okay, so this is the categorization. Then I will describe the end of this presentation, the squeezed state, what is really physically meaning. Then I will tell you it towards the end. Okay, let's go one by one. Basically, the Fock state is a very fundamental one, which is a quantum state with a very well-defined photon number. It's a very exact. Okay, so suppose if you say that if you have only one photon, it's only one photon. So these states are usually represented by this n, which is a n. The n cap, which is a number operator, which is defined in the quantum harmonic oscillator, is A dagger A. So here A is an annihilation operator and A dagger is the creation operator. So if n is being acted on n, so you say A dagger A acted on n. So A act on n, what will do is that it will make you square of n minus 1. And again, A dagger act on that n minus 1, you are going to get again square root of n. Therefore, you are going to get a n eigenvalue. So where this n is this is the number of photons. When you have a 0, what is the physical meaning of 0? So when you say n is being 1 is being 1, it makes sense, right, physically. So that means that you have a 1 photon. When you say 10, it makes that you have a 10 photons. What does it mean when n is being the 0? So n is being the 0 means it's a vacuum state. Okay, it's a vacuum state where there is no photon. Okay, it's represented as a 0. So then in the so nth excited state, in terms of the ground state, which is a n is the 0, then you can write when you have a n is, suppose if it is a, if you want to go to the first excited state, then you can apply n is being 1, then you can go to the ladder operator, but to ground state to the excited state. So then or the first excited state to second excited state. Okay, so the number, the photon number, it's a fixed number. There won't be any variance because it doesn't fluctuate. The photon number doesn't fluctuate. Therefore, delta n is being 0 because since your n bar is 0, because it doesn't fluctuate. It's a fixed number. So how to realize these states experimentally, which makes often difficult for the experimentalist, as I said, that you need to find a single atom. So you need to find a single ion, you need to find a single molecule, or you need to find a single quantum dot, or you need to find a single vacancy centers in diamond, which makes experimentalists very tough, because conventionally most of the experiments are done that millions of atoms or the millions of ions or the millions of molecules or the millions of any other emitters. So isolating one is often difficult. Therefore, experimentally realizing the Fock states are very difficult. Okay. So the vacuum states, as I just now described, with is a special case of the Fock state, which is basically no photon. So once you have a no photon, then you know what is the 0-point energy, which is a of h plus omega. And you may think that when you're saying that no photon, how the energy is coming. Okay, it is there is a vacuum. Okay, there is a fluctuation of the electric field. It's a vacuum field. Okay, so that's why you see that there is an energy which is a half h cross omega. So this field is always present even in a complete vacuum. I mean, everywhere it is there, everywhere, this vacuum fluctuations. That's why you see that when you are coupling the atoms, when you are exciting the atom from the ground state to excited state, then in order to come from the excited state to the ground state, so what does is that it loses the energy and it will come back. So if the atom is losing the energy, means which the energy is taking, the atom surrounding is taking, which is a vacuum. So it will create a fluctuations in the vacuum, or it will give to the system outside the atom, then it will decay. Without losing the energy, it cannot come down. This is usually, it is called spontaneous emission in the case of two-level atom or any other level atom also, which I think that I hope you know that part. So that is the number state or the Fock state. Now this is the more convenient, or the more often you see in the real life, is the coherent states, which is it is basically monochromatic electromagnetic wave, which is a laser light. So essentially the eigenstates of this annihilation operator is a coherent state. Okay, so in the if A is act on alpha, so it would give you the alpha is your eigenvalue with a alpha, where this alpha is represented as a coherent state. You can say that the coherent state is the eigenstate of the annihilation operator. So in the photon number representation, the coherent state is defined in this way, which is alpha is e raised to the power minus mod alpha square by 2 is sigma is ranging from this alpha raised to the power n by n factorial. Then you see here is where n is being sitting here. The coherent state is basically, you can think of the superposition of the Fock state or the number state, right? So you see where the n is being with different probabilities. What I mean is, when if you place n is being 0, then n is being 1, then you can say that what is a 0 photon probability, what is a 1 photon probability, and what is a 2 photon probability. It's a superposition with a different amplitudes, right? So the coherent state can be described in this form. It can be superposition of the number state, you can say, or the eigenstate of the annihilation operator. And importantly, so unlike like a number state, the coherent state doesn't have a fixed photon number. So the photon number, it gets fluctuates, because you can here you can clearly see that n, the value which is being running from 0 to infinity, it has all possible with different photons. So when you measure number of photons each time, so you will know how many photons are being present in the coherent state. This is the important point here, is that the number states, or let's say if you put 1 and 1, that is 1 and 1 is obviously non-zero, but it's give you 1 and 0, or 1 and 2 are in the case of number states are 0. These are the basically orthogonal in the case of number states. But whereas the coherent states are not orthogonal. So suppose if you have a beta and alpha, if you take a inner product, it's non-zero. Okay, this is the most important thing, because if you see here, when you take an inner product with beta, so this will, here also you will get a beta factor, and also you will get a beta star all raised to the power n. So it doesn't going to be a 0. So which means that coherent states are not usually in orthogonal. So that's the point. And the photon distribution, as I said, it follows the Poissonian distribution. Okay, so if the Pn, if you find the probability from the state which is given in the coherent state, so you are going to get a Poissonian distribution. So which is basically where this is in this form. So if you say n equal to 0 or 1, so you will find where the maximum probability. So obviously when n equal to 0, it has a maximum, so you can see it all depends on what is the average number of photons, because if the as per the, you see, we have divided the statistics when the uncertainty or the variance or the standard deviation is equal to the average square root of average value, then this have a Poissonian distribution. Okay, so often these examples are in experiments are seen. The Poissonian distribution is that the laser is the best example for the coherent state. So when you measure this state of light for the laser, you often get coherent states. Again, I repeat here, people often confuse again that when they think that using the alpha, you are able to generate a number state. So what they think is that, suppose let's say that if it's a n is being 1, then you will have a, here is 1, right? So that's a 1 photon probability. So but in the coherent state, not only 1 photon probability, 0 photon probability also there, and 2 photon probability also there, 3 photon probability also there. So you can never converge, no matter what you do experimentally, coherent state to be coming to the number state. That's the essential difference. Unless you change the source itself, you change the source from the laser to the single photon source, then your statistics from the Poissonian statistics to sub-Poissonian statistics, it can be changed. That is the essential difference between the coherent state and the number state. Okay, then another state which we described, that's a superposition statistics. So which is a basically thermal state, which is an incoherent light emitted from a source in a thermal equilibrium, such as the black body radiator or the tungsten or the sun which is coming. So which means that what happens is that the number of photons coming in the statistics are coming as a bunch, because it is coming completely random. So when it's a phase and amplitude and all the things, it fluctuates very drastically. So, and also the arrival times of the photon wherever you do the measurement is entirely different. So therefore this follows a statistics which is like a Bose Einstein statistics. This statistics it follows where n is equal to 0 and 1 and 2. So when you take a variance, so in the case of the coherent light, when you take a variance, that is equal to n bar. Okay, so that is the first term is due to the quantization of energy of the electromagnetic radiation, and the second term, okay, so if this one is 0, then this would have been a coherent state. The second term which is coming, that is a noise. It is due to the noise, because it is coming randomly with fluctuating the photons and the fluctuating the intensity, which is basically number of photons. So there is an additional term which means that in the variance compared to the coherent state, in thermal state is more. So therefore the spread of the photons would be more, because that's where the physical meaning of the variance, the photon number fluctuates quite drastically. So here I summarized the photon distribution statistics. How physically, when you are trying to measure the photon number, so how the it looks in the measurements. Suppose if it is a Fock state, okay. So Fock state, as I said, it is a definite state. You have a fixed number of photons, right? So the n average, which is a n bar, is, let's say, that is a 1. Then you have a photon at n equal to 1 only. There is no probability. So there is no probability other than this n bar equal to 1. So that means that one photon is coming with 100% probable. You see here. Okay. So 100% probability that you will have only one photon. That's why in experiments often difficult to generate this state. And when you say n is being 5, then you see it's definite that you have this many with a 100% probability. In contrast to the Fock state, if you say the coherent state, you see this where n bar is 1, then you see that at a different photon number, it contains at different probabilities. Okay. So sometimes people say that the quasi Fock state, the coherent state, because they say that if you attenuate the number of the photon, okay, in experimentally, like say 4 you can make it 3 or you can make it 2, so you can so that you will have more probability at 1. But when they say that quasi, then that's not perfectly correct when they mention that. So the coherent state never become a Fock state unless you change the source itself. Okay, so you understand the essential difference. This is the essential probabilities. When you say the Fock state, when it's coming from the single photon source, you are definite that you have only one photon, which is, or you have a definite number of photons which are coming with 100% probability. Whereas in the case of coherent, so you see that some of them will have the 30%, 35% probability, and some of them you have 20% probability. Some of them you have less than 5% or 10%. So when you shift this, if you want to shift the maximum, so you can change the average number of photons to 5, then you can see the Poisson distribution on both the sides, which is centering at 5. Okay, it's because your coherent state distribution depends on the n bar. So the n bar can be average photon number can be it can vary from 1 to 5 or 1 to 100 or whatever the thing. And in the case of thermal state, so you can see that it follows So similar like a exponential. So you see that it is drastically changes in the when the photon number increases, you have a uh, less probability. So this is also not this is, which means that most of the photons are coming at once. So then next is coming at different probabilities. As you increase the number of the average number of photons, the probabilities are at zero, and other one photon probability is coming low, because you don't find the definite number of photons in this thermal state. So then the question is, how do you measure experimentally? So far, this is what it is done is the theory, or the I would say it's mathematical formalism, which was developed for the based on the photon statistics. You have divided into the Fock state and coherent state and thermal state. But now let's say that you have given one source or the light. So then you ask you to find the about that light information in the in terms of which state it is. Either it is a Fock state, or it is a coherent state, or it's a thermal state. Okay. So you are asked to find. So how do you know? So now you have to perform the experiment, which is very, very important. It's a powerful experiment which was proposed by this Ambry bound twist setup for measuring the photon statistics. What it measures physically, I will tell you that it measures the second order correlation, which is a Z2 tau. Tau is the delay time between the two channels. Okay, so here, so suppose you don't know whether you placed here Fock state or the number or the coherent state or the thermal state. So some beam of photons are coming. So you place a beam splitter, okay, 50-50 beam splitter. So then your transmission goes to the detector 2, and reflection goes to the detector 1. Okay, and you are measuring the coincidences at this place. Okay, so now if the photons are coming, obviously it will split this way and this way, depending upon the what are the source, depending upon the source characteristics. Okay, so what is basically measures is that N1, suppose this is the N1 which is coming at T, and N2 of T plus tau, the delay between these two channels, okay, the delay between the two channels. So what is the detection of the probability of the photon? So suppose if N1 of T is there, so after let's say 100 nanosecond, what is the probability of detecting the photon at D2? That's what the top term, and average of each photon number in the channels. So because you need to normalize the signal, so this is the average between the N1 and N2. This is individual average of N1 and N2. So because suppose some 100 photons are coming, so you see 30 photons are this side, and let's say that 70 photons are this side. So the total number has to be the conjunct. So you have to normalize. Okay, so that you will see the clear signature. So it is basically the probability of detecting the photon after certain time. Okay, this is the essential point. So this is the proposed sometime 1956. Then let us say that you have a subposition light, which is called, it's an anti-bunched light. Okay, it is a subposition statistics, which is a single photon source. It's an anti-bunched light, it is called. I will tell you why it is called anti-bunched. So for that you have to understand bunched. Okay, bunched means it's a thermal state, it will come. So as I already mentioned, in the Fock state or the number state, all the time you have a definite number of photons. Definite number of photons all the time, no matter. Okay, all the time you have a definite number of photons. Suppose this photon comes and hit beam splitter. Okay, so as you know, quantum mechanically, so it will be detected either D2 or D1, because photon cannot be splitted. So either it will go to the D1 or D2. Then if let's suppose they say that it goes to the D1, then you take a correlation. Okay, when you have a delay time, what is the probability of finding the photon here? It's 0. Okay, at 0 delay you will see 0. Okay, so when you see at 0 delay is 0, that means that you have a anti-bunched light, which is a sub-Poisson statistics. Okay, suppose if the second photon comes and goes straight away D2, then simultaneously you are not able to find the D1. There is no photon at D1. Therefore, if you take a coincidences, again you will see 0. Then from 0 to the 1, which is a probably after certain time, what happens is that it will the separation between the two photon events is decided by the excited state lifetime of the atom or the single photon source, which is coming from the source. So after this lifetime is over, then there is no correlation between the photons which are coming here and which is coming here. Okay, so this is at 0 delay is 0 is observation is a signature that you are seeing the non-classical nature, which is a Fox state. Okay, this is the point. When it comes to the coherent, which is coming, the photons are coming quite randomly. Sometimes you get 1, sometimes you get 2, sometimes you get 1, sometimes you get 2, sometimes you get 3. You see that randomness. As a result, what is happening is that if the photons comes and hit, okay, always there is a coincidences between the D1 and D2. There is no dip at 0 delay because it is coming randomly. If the 2 photon comes, 1 goes here and 1 goes here, or if it is a 3 comes, 2 goes here and 1 goes here. Okay, so therefore what you see is that over the time, this is the time axis, sorry, it was not mentioned, it's the time axis, that you always see Z2 is 1, Z2 tau is 1, which is a signature of the Poissonian statistics, which is a coherent light. Okay, when you have a Poissonian statistics, you will see there is no correlation. There is no correlation between the photons which are coming from the source. Now let us say that the bunched one. Okay, before as I said anti-bunched one, it's a bunched one is that which is the thermal light. You see flood of light, right? For any lamp, if you say thermal source, then you will see flood of light. So that means that many number of photons are coming together. Okay, not one, not 0, and not 2. Many. It's coming as a bunch. So what happens is that if the let's say that if it comes this photon 10 comes and hit here, so some of them will transmit here, some of them will reflect here. When you take a coincidence measurement, what is going to happen is that at 0 delay, since it's coming as a bunch, so you will see the peak in the at t equal to 0. Okay, after certain time it decays because again it depends on the what is the lifetime of the state of that particular source which you use the thermal source. Okay, so then it will all the curves will converge after long time to the coherent source, which means that the photons are coming over the long time randomly. Okay, so you must clearly understand this. This is the essential difference between the Fox state, which is an anti-bunched light, and this is the coherent state, which is a no correlation, which is a Z2 tau is a 1, and it is a bunched light, which is basically the superposition. This is what it's called superposition. It is a Poissonian. It's a sub-Poissonian. Okay, so experiments are measuring for the bunched light is easier because you do often you get thermal states. If you switch on any light, then you will get bunch of photons. You can send it through these measurements, and you can basically measure the correlation between them. This is much easier. So the coherent source, which is a laser, measuring the correlation between for the coherent laser also easier because nowadays we get a laser. I mean, in every I think typically in all the places. Okay, so generation of the bunched one and coherent one is easier. But the difficult one is anti-bunch. The reason why it is called it's anti-bunched is that when you have a bunch of photons, it follows the reverse. This is a bunch coming because a bunch of the photons are coming and hitting the detector. And here, whereas the anti-bunched means only one photon is coming at once. So the top two is often very easier to perform the experiment. The bottom one, which is the anti-bunch, is difficult to do the experiments. Okay, so therefore I don't describe much on the top two because that is most of the people are doing and most of the research has been done on that. So I am going to show you how to measure the anti-bunching. Like this is the setup what we set up in the in our lab. Okay, so please remember that the photons which are coming is a one photon. Okay, please remember. So that means that your detectors, whether this D1 and D2, should be sensitive enough to detect one photon. Okay, that is the most important thing. So these are the APD1 and APD2, which we use it for the these are called avalanche photodiodes, which can detect one photon at a time. These are called SPCM. So single photon counting modules. Okay. So these two detectors are. So to perform this experiment, you need two detectors that you have to remember. Single detector cannot do this photon statistics. So you need a two single photon detectors. And what you need a beam splitter. So you see here, there is a beam splitter, which is a very micro component, which I will expand next click. And you need a photon correlator, which is a counter and the timer. This is what the counter and the timer. Okay, if you see it here, the input comes and this is the beam splitter. This is a micro optical component in our lab which is being used. The purpose is that we can shift this this setup from our lab to anywhere in the country, so that one can measure the photon correlation for all the lights which is available in the particular place. Okay, the input is splitted into two beams. So this is the beam splitter. So the one will go to the this detector, another one will go to the this detector. So once you detect the photons, the correlation, because these detectors will generate the electrical pulse. Okay, so the one photon comes and hit here, and it is converted into the electrical pulse. Then electrical pulse is fed to the correlator. So you have a four channels and the correlator. So we use only two channels for the performing the photon correlator. This is the state of art experiment which is being performed in our lab. So if you have a two detectors, then this you can see this bidirectional histogram, which is basically to build this kind of a photon anti-bunching behavior. Okay, so if you use a for the same setup, if you use a laser, you would see the flat one. For the if you use a incoherent source, which is basically thermal source, then you will see the bunched one. That is not much more interesting because it's it's a both two states are it says it's a non-class classical states. It's only the non-classical is the anti-bunch states, which is the true quantum nature of the light. Okay, this is the how the experiments are done, and I want to emphasize that to work with the Fox states and number states are extremely difficult, extremely sensitive, because just imagine that. I just want to give you the example that, as I said, most of the people or most of the groups working in the world as well as in our country, that they work with more than millions of photons. Okay, just I want to give, then you know the E equal to H nu, right? So here, generally, if you put E equal to NH nu, you are probing the N is being 1. That means the single atomic transition you are probing. That is the essential point. Where N is, let's say, in the other cases, it is a 10 raised to the power 6. But in our case, it's a only 1. That is where the challenge lies. We are manipulating the Fox state with only one photon. Otherwise, we will not be able to generate the Fox state or the number state. So mathematically, description for the Fox state is easier, but experimental realizations are extremely difficult, because such system to realize it is massive efforts are required. Okay, so we are working towards that. At the end of it, I will show some more facilities what we have. So how to kind of manipulate the Fox state, I will show you, because this, since it's a context has come, I have shared. Okay, so, and importantly, these often people find that this optical components are in the sizes of inches, but in our lab you find that it's more compact. It's a total optical table size is only 10 centimeter by 10 centimeter, so it's very compact. Okay, so based on that experiment, so the classification you can say, as I said, when you have a Z20, which means that when you have a time delay is 0, okay, so then you say that if the bunched light Z20 would be more than 1. So because it's a light is coming as a bunch, therefore you will see that probability is higher. And when you have a coherent light, when Z20 is 1, so there is no correlation. So for the, let's say for the laser light, so when it goes to the anti-bunch light, which generates the number state, this is the bunch light is the thermal state, and this is the coherent light is the coherent state, and the anti-bunch light is the Fox state. Then when you have a Fox state, which is a single photon non-classical behavior, you see at Z20 is less than 1, which is basically, ideally speaking, Z20 should be 0. Okay, that is theoretically. But let's see what are the experimental challenges when you measure. So first we'll talk the experimental demonstrations of the anti-bunching. So because these anti-bunching was measured in 1977 by the Professor Jeff Kimball. He is a professor at Caltech. So he uses the atoms, okay, ensemble of atoms, and out of which he separated the single atom. Okay, so in order to see the anti-bunching nature, so you need to isolate his individual emitters. Okay, so that could be a one atom. Just imagine we are talking only one atom. Okay, just or one molecule or one quantum dot or any color center. Okay, so then only you will be able to see this anti-bunching measurement. Okay, so otherwise it's a washed off, so you don't see true quantumness in the experiments. These experiments are often difficult. This is the setup which I have described. They have used at 1977 this kind of a setup. So they have 2 detectors and they are doing the measurements. Then you see here, this is the delay time and this is Z2 tau. Okay, so then you see this is the fitting curve, the solid one. It goes like this. The experiment is at Z20 is a non-zero. Okay, so it's theoretically you expect that Z20 is a 0, then provided you have only one atom. If you have more than one atom, you would not expect to see Z20 is 0. So that means that when you are working, the atom is a very small, tiny, right? And atom does not stay at one place. It's always flies around. Okay. So they have used the sodium atomic beam atoms, and they isolated close to one atom. Okay, close to one atom. Therefore, you can see Z20 is less than 1. This is the experimental point. Okay, so that's why they can generate the Fox state or the number state in such kind of a systems. Okay, so then after this, why only atom? Okay, atom is a natural emitter. Okay, natural emitter in the sense that everywhere the atoms are there. So, and in the case of atom, it's extremely difficult to kind of handle the experiments, because it's only one atom. Okay, it's you need a lot of intense technology, a lot of funds to kind of technically it's very challenging to do that. But later people thought if there are any other emitters where we can get easily the single photons, then they are thought of like a solid state quantum emitters. Solid state quantum emitter, for example, semiconductor quantum dots. This quantum dots also it's an ensemble of atoms. Okay, but it's not one atom, it's an ensemble of atoms. So handling ensemble of atoms, it's easier compared to the handling of a single atom, right? So, but it's a quantum dot. The levels are well quantized, okay? But it's also this quantum confinement comes from the size of the emitter. So then people started working on it. It's in late in 2000. Then indium arsenide quantum dot. Then they place it. Then they isolate it single. Then they perform the Hambre boundary setup. Then they saw that at zero delay, still they are not getting perfectly zero. That means that you see how difficult the experiments are, because even the quantum dot, when you make an ensemble of atoms, which makes the quantum dot, but still it is tough to kind of generate a pure single photon source or the pure Fock state. But the signature of the signal, because your Z2 0 is much less than 1, therefore this source is a sub-Poissonian statistics. So if you use a laser, you will see there is no dip here. You will see like this. Okay. If you use a thermal light, you will see like this. There is there will be a bunch. Those two experiments are easier. Sending laser into the setup is easier because that's readily available. Sending a single photon source is somewhat difficult. Okay, that's what I am kind of emphasizing. Okay, so you see Z20 is 0.2. It's a clear signature that anti-bunching light is there, but pure single photon source yet to be realized. Okay, people are now trying. It's like a 0.1 or 0.01 we could reach, but still state of the art. What ideally you want to be really zero. That's what people are trying for, so that you can really generate the Fock states. And importantly, these measurements are done at 4K because you have a indium arsenide semiconductor system. You need to have a low temperature atmosphere because you need to have kill the phonon contribution. Okay, so in our lab, what we are working with the semiconductor quantum dots as well as the color centers in nano diamond also we are working. So later the other quantum emitters, not only the atom, because as we have seen that the atom experiments are extremely difficult, and in the world only we can count the people who are working on the single atom is only less than 10. Okay, in India maybe one group is working on only single atom condition, but whereas in the other type of quantum emitters in the world maybe 10 to 15 groups are working. So in India only 2 or 3 groups are working in other type of quantum emitters. Recently many people have started working on this because of this national quantum mission need a quantum source that where it can give the Fock states, then it can be useful for the various applications in the quantum technologies. I think I will stop for 5 minutes and I will get back to the next topic. Can I stop?
Okay, sure, sir.
Yeah, I hope.
Yes, sir.
Yeah. So I'll start again at 3. Am I right?
Yes, sir.
Yes, you can
Yeah.
start 3 or so.
Fine, right.